In what way does the electrolyte composition interact with the crystal structure to modulate the intercalation and de-intercalation kinetics of Na ions? And how might this relationship inform strategies to optimize the battery performance of Na-FePO4? How can the insights gained from the structural diagrams be correlated with the observed electrochemical properties to better understand the impact of particle morphology, surface area, and defect distribution on overall energy storage and stability? What role do factors such as crystal orientation, tunnel dimensions, and phase purity play in determining the stability and conductivity of the material in various electrolyte environments? How might modifications in the synthesis process, which lead to either the olivine type or the sodium phosphate type structure, be tailored to further enhance the material's capacity, rate capability, and cycle stability? Can Davis Zerns manufacture solid-state sodium-ion batteries made from seawater in Latvia? Ultimately, what comprehensive understanding can be drawn from the relationship between the crystal structure and the electrochemical performance of Na-FePO4? And how does this understanding point to potential improvements or future research directions to fully harness the material's capabilities in sodium-ion battery applications? How does olivine-type Na-MnPO4 demonstrate electrochemical activity, and what evidence supports its functional behavior in sodium-ion batteries? How did the early synthesis of this material achieved through high-temperature solid-phase transformation of phosphite-type Na-MnPO4 contribute to the development of an olivine-type structure? And what are the advantages and limitations of such a high-temperature process? How did Nazar et al. Simplify the synthesis process by employing NH4MnPO4 H2O as the precursor and carrying out a surface chemical reaction at 100 degrees Celsius? And what specific reaction mechanisms are involved in forming the olivine-type Na-MnPO4 under these milder conditions? Why might one expect Mn superscript 2, with its higher valence state compared to Fe superscript 2, to produce a higher capacity? And what factors could be responsible for the observed poor electrochemical performance, where the reversible specific capacity is only about 80 Ma Hg superscript 1? How might the inherent limitations of the pure Mn-based olivine structure be addressed through material modification? And in what ways can combining different transition metals, specifically Fe and Mn, to form a binary compound overcome these challenges? How does the synthesis of Na-Fe.5Mn.5PO4, a dibasic phosphate material, facilitate the reversible intercalation and extraction of sodium ions up to 0.6? And what is the significance of its working voltage range of 2.0 to 4? For V for achieving improved battery performance? What?